There's something achingly beautiful about the way the universe taunts us, dazzling us with wonders just out of reach, like fireflies flickering in the night, always one step ahead of our grasp. Picture this: colossal structures, some stretching hundreds of millions of light years across, woven into the fabric of space itself, cosmic masterpieces we can see but never touch, mysteries whispering to us across the void. These are not just distant objects, they're enigmas that defy our understanding, bending the laws of physics and teasing the limits of human imagination. And today, we're setting off on a journey to explore 25 of the most extraordinary among them, structures so vast, so strange, they might as well be from another dimension. Think about that feeling when you stand beneath a starry sky, humbled by its infinite depth. Now imagine that same awe, but magnified 1,000-fold, as we unravel the secrets of cosmic giant supervoids where space itself seems hollow, filaments of galaxies threading through the universe like strands of a spider's web, and quasars blazing with the energy of 1 trillion suns. These aren't just scientific curiosities, they're the universe's way of showing off, reminding us how much we still have to learn. Every one of them holds clues to the grandest questions. How did the cosmos come to be? What strange forces sculpted these impossible shapes? And why do they linger just beyond our reach, like a cosmic carrot dangling before us? This isn't just a tour of distant wonders, it's an invitation to stand at the edge of human knowledge and peer into the unknown. By the time we're done, you'll see the night sky differently, not just as a blanket of stars, but as a canvas of unsolved riddles. Some of these structures are so immense they warp the very space around them. Others flicker in and out of existence like ghosts, but all of them share one tantalizing trait. They're out there, waiting, challenging us to keep looking, keep questioning. So let's begin, because the universe has 25 secrets to share, and they're more breathtaking than you could possibly imagine. Hidden behind the thick veil of our own galaxy's dust and stars, there's something out there tugging at us, an invisible force so powerful it's dragging entire galaxies, including our own Milky Way, toward it at staggering speeds. This is the Great Attractor, one of the most baffling mysteries in modern astronomy. Imagine throwing a ball into the air only to watch it suddenly curve sideways, pulled by some unseen hand. That's essentially what's happening to galaxies across our cosmic neighborhood, all drawn toward a point roughly 250 million light-years away, deep in the constellation Norma. But here's the catch: we can't see it directly. Our view is blocked by the so-called zone of avoidance, a region of the sky obscured by the dense gas, dust, and stars of the Milky Way's galactic plane. It's like trying to peer through a sandstorm to spot a distant lighthouse. What makes this cosmic tug of war even stranger is the sheer scale of the force at work. The Great Attractor's gravitational pull is so intense that it's influencing thousands of galaxies, including ours, with a collective motion of hundreds of kilometers every second. For decades, astronomers struggled to explain what could wield such power. At first, they thought it might be a massive supercluster of galaxies, a dense knot of cosmic structures bound together by gravity. And they were partly right. The Norma cluster, a colossal gathering of galaxies, sits near the heart of the Great Attractor. But here's the twist: even that isn't enough to account for the full strength of the pull we're experiencing. There must be something else lurking behind it, something even more massive and mysterious. Some scientists speculate that the Great Attractor could be just the tip of an even larger iceberg, an enormous concentration of dark matter, or perhaps a remnant of the universe's early structure, a relic from when the cosmos was still stitching itself together. Others wonder if it's connected to something called the Shapley supercluster, an even more distant and massive congregation of galaxies that might be amplifying the pull. But until we develop telescopes capable of seeing through the Milky Way's dusty curtain, the Great Attractor will remain an enigma, a cosmic siren calling us toward a truth just out of reach. What's thrilling is that this isn't just a story about distant forces, it's a reminder that the universe is dynamic, alive with motion. Right now, the Milky Way, Andromeda, and countless other galaxies are racing toward the Great Attractor, caught in a river of gravity that began flowing billions of years ago. And though we might not yet know what's waiting for us at the end of that journey, one thing's certain: the universe loves a good mystery, and this one's among its greatest. If the Great Attractor is the universe's way of pulling us toward the unknown, then the Boots void is its opposite, a yawning chasm of nothingness so vast it defies logic. Stretching over 330 million light-years across, this enormous region of space is eerily empty, a cosmic desert where galaxies ought to thrive but don't. Astronomers call it the Great Nothing, and it's one of the largest voids ever discovered, a gaping hole in the cosmic web that leaves even the most seasoned scientists scratching their heads. Picture the universe as a bustling city with galaxies clustered like neighborhoods, connected by filaments of gas and dust, the streets and bridges of the cosmos. Now imagine stumbling upon a district so desolate it stretches farther than the eye can see, silent and abandoned. That's the Boots void. When it was first detected in the 1980s, researchers expected to find thousands of galaxies within its borders, but instead they counted fewer than 60. To put that in perspective, a typical region of space that size should host at least 10,000 galaxies. The sheer absence of matter here isn't just unusual, it's borderline unnatural. So what could carve out such a void? One theory suggests it's the aftermath of an ancient cosmic collision, where smaller voids merged over billions of years, leaving behind an emptiness of staggering scale. Others speculate it might be evidence of exotic physics, perhaps a tangle of dark energy or a gravitational anomaly left over from the universe's birth. Then there's the unsettling possibility that the Boots void isn't empty at all, but filled with something invisible, something our telescopes can't detect. Dark matter, for instance, could be lurking there in massive quantities, exerting its pull without emitting a single photon of light. But here's the twist: even voids like this one aren't completely barren. The few galaxies that do call the Boots void home are bizarre in their own right. Dubbed wallflowers of the cosmos, they're isolated, lonelier than most, forced to evolve in an environment devoid of galactic neighbors. Studying them could reveal how galaxies behave when stripped of the usual gravitational influences, like watching a child grow up on a deserted island. The Boots void challenges our assumptions about how the universe structures itself. Is it a statistical fluke, a rare quiet corner in an otherwise crowded cosmos? Or is it a clue to something deeper, a sign that our understanding of gravity, dark matter, or even the Big Bang itself is incomplete? Every time we peer into this great nothingness, it stares back, reminding us that the universe isn't just a collection of stars and planets, it's a puzzle, and some of its pieces are still missing. Just when you thought the universe couldn't stretch our imaginations any further, along comes the Hercules-Corona Borealis Great Wall, a galactic behemoth so vast it makes earlier cosmic giants seem almost quaint. Imagine a structure so immense it spans roughly 10 billion light-years, a filament of galaxies threading through the cosmos like a celestial serpent. To put that in perspective, if you could travel at the speed of light, it would take you longer to cross this single structure than the current age of our entire universe. That's not just big, that's universe-breaking big. Discovered in 2013 by astronomers mapping gamma-ray bursts, the most violent explosions in existence, this great wall defies everything we thought we knew about the cosmos. According to the cosmological principle, the universe should look roughly the same no matter where you observe it from, a concept known as homogeneity. Matter should be evenly distributed on the largest scales, like a perfectly mixed cosmic soup. But the Hercules-Corona Borealis Great Wall throws a wrench into that idea. Here's a structure so colossal it shouldn't exist under our current understanding, a glaring exception to the rule. What makes this even more fascinating is how it was found. Gamma-ray bursts, often caused by the deaths of massive stars or collisions of neutron stars, serve as cosmic breadcrumbs marking the locations of distant galaxies. When researchers noticed an unusual concentration of these bursts in the direction of Hercules-Corona Borealis, they realized they were looking at something monumental, not just a cluster of galaxies, but a sprawling, interconnected network stretching across a tenth of the observable universe. The implications are staggering. If structures like this exist, it means the universe might not be as uniform as we've assumed. Some scientists speculate that the Great Wall could be a remnant of primordial density fluctuations from the Big Bang, regions where matter clumped together more intensely in the early universe. Others wonder if we're seeing evidence of exotic physics, perhaps the influence of dark energy, or even a flaw in our understanding of gravity itself. And then there's the unsettling question: is this the biggest structure out there, or just the biggest we've found so far? Every time we push the boundaries of our telescopes, the universe seems to reveal another layer of complexity, another challenge to our assumptions. The Hercules-Corona Borealis Great Wall isn't just a curiosity, it's a cosmic rebellion, a reminder that the universe still holds mysteries too big for our textbooks. And if something this colossal can hide in plain sight, what else is waiting to be discovered? Among the countless galaxies adorning our universe, Hoag's object stands out like a cosmic bullseye, a perfect ring of vibrant blue stars encircling a golden core, so symmetrical it almost looks artificial. Discovered by astronomer Arthur Hoag in 1950, this celestial oddball defies the typical spiral or elliptical shapes we associate with galaxies, presenting instead a stunning, almost hypnotic circular structure. At first glance, you might mistake it for a galactic collision frozen in time, or even a trick of perspective. But Hoag's object is very much real, and its existence challenges our understanding of how galaxies form and evolve. What makes this ring galaxy so mesmerizing isn't just its beauty, it's the mystery of how it came to be. The core, packed with older, yellower stars, resembles a typical elliptical galaxy, while the outer ring blazes with young, hot blue stars and active stellar nurseries. Stranger still, the space between them is nearly empty, a dark gap devoid of the stars or gas you'd expect to see bridging the two regions. One leading theory suggests it's the aftermath of a galactic collision billions of years ago, where a smaller galaxy punched through the center of a larger one, sending shockwaves rippling outward like a stone dropped in water. These waves could have compressed gas and triggered star formation in a perfect ring, leaving the core relatively undisturbed. But here's where the plot thickens. There's no obvious sign of a surviving intruder, no debris trail or secondary core that would typically litter the scene of such a crash. Some astronomers argue that the collision must have happened so long ago that all traces have vanished, while others propose a far stranger idea, that Hoag's object formed through an entirely different process, one we haven't even identified yet. Could it be the result of gravitational instabilities, where the galaxy's own rotation sculpted the ring over eons? Or is it evidence of something more exotic, like the influence of a massive black hole's jets shaping the surrounding gas into a perfect circle? Adding to the intrigue, Hoag's object isn't entirely alone. A handful of other ring galaxies exist, but none as pristine or symmetrical. Even more peculiar, if you peer closely at the void between the core and the ring, you'll spot another faint, distant ring galaxy, almost like the universe is teasing us with a nested cosmic mystery. This raises another tantalizing question. Are these rare structures flukes of nature, or is there some fundamental yet overlooked mechanism that occasionally births them? Studying Hoag's object is like uncovering a single page from a galactic instruction manual we've yet to fully read. It forces us to reconsider the violent, chaotic processes that shape galaxies and whether serenity, not just collision and chaos, can carve such perfection. Every time we observe it, we're reminded that the universe has a flair for the unexpected, crafting rarities that humble our assumptions and spark new questions. And in that way, Hoag's object isn't just a curiosity, it's a cosmic conversation starter, inviting us to rethink what we know about the stories galaxies tell. Deep in the fabric of the cosmos, something strange is stirring, a mysterious current pulling entire galaxy clusters in a direction that shouldn't exist. Astronomers call it the dark flow, and it's as if the universe has a hidden hand guiding matter toward some unseen horizon. Picture a river flowing silently through space, carrying thousands of galaxies like leaves caught in its grip, all moving toward a destination we can't see or explain. This isn't just random motion, it's a coordinated drift on a scale so vast it challenges the very foundation of modern cosmology. The story begins with galaxy clusters, colossal gatherings of hundreds or even thousands of galaxies bound together by gravity. When scientists studied the motion of these clusters using the cosmic microwave background, the afterglow of the Big Bang, they noticed something bizarre. Instead of moving randomly, these clusters seemed to share a common velocity, streaming toward a single point in the sky near the constellations Centaurus and Vela at speeds exceeding 1,000 kilometers per second. What's unsettling is that this motion can't be explained by any known gravitational force. Not the pull of nearby superclusters, not the Great Attractor, not even the immense Shapley supercluster. None of them can account for this relentless, synchronized movement. So what's causing it? One spine-tingling possibility is that the dark flow is evidence of something beyond the edge of our observable universe. Imagine standing on the shore of an ocean, watching the waves roll in, but realizing the tide is being pulled by something far beyond the horizon, another ocean, perhaps, or a continent we've never seen. Some theorists suggest the flow could be the gravitational tug of massive structures outside our cosmic bubble, regions so distant their light hasn't had time to reach us in the nearly 14 billion years since the Big Bang. If true, this would mean our universe is even larger and more complex than we ever imagined, with entire realms of matter lurking just out of view, but not everyone's convinced. Skeptics argue the dark flow might be an illusion, a statistical fluke, or a distortion in our measurements. Others propose a more radical explanation, that the flow hints at flaws in our understanding of gravity itself. Einstein's theory of general relativity has been the cornerstone of cosmology for over a century, but what if it's incomplete? Could the dark flow be evidence of exotic physics, a fifth force, or perhaps a modification to gravity that only reveals itself on the largest scales? The idea isn't as far-fetched as it sounds. Dark energy, the mysterious force accelerating the universe's expansion, was once just a wild hypothesis too. Here's where it gets even weirder. If the dark flow is real, it could mean the universe isn't as uniform as we thought. The cosmological principle, the idea that matter is evenly distributed on large scales, might need revising. Instead, the cosmos could be lumpy, with imbalances stretching far beyond our field of view. Some researchers have even floated the idea that the flow could be a relic of the Big Bang itself, a cosmic fingerprint left by the violent, asymmetric birth of space and time. Whatever the truth, the dark flow forces us to confront the limits of our knowledge. It's a reminder that the universe is still writing its rulebook, and some chapters might be waiting in the darkness just beyond our sight. Whether it's unseen matter, new physics, or something even more extraordinary, this enigmatic current is pulling us toward a startling realization. The cosmos still has secrets, and they're drifting just out of reach. Rising from the heart of our galaxy like two colossal balloons of energy, the Fermi Bubbles stretch 50,000 light-years into space, one erupting above the Milky Way's disk, the other below, each glowing with the faint but unmistakable signature of gamma rays. These vast, ghostly structures, discovered only in 2010 by NASA's Fermi Gamma Ray Space Telescope, are a cosmic wake-up call. even our own galactic neighborhood harbors mysteries we've barely begun to unravel. Imagine two symmetrical geysers of high-energy particles shooting from the galactic center, their edges crisp, their presence so immense they dwarf the Milky Way's spiraling arms. Yet despite their scale, they were invisible to us for centuries, hidden in plain sight until we learned to see the universe in gamma rays, the language of the most violent events in existence. What could launch such enormous structures? The prime suspect sits at the very center of our galaxy, Sagittarius A, the supermassive black hole with a mass 4 million times that of our Sun. Astronomers suspect the bubbles are remnants of an ancient frenzy, a time when Sagittarius A wasn't the quiet giant it is today, but a ravenous monster devouring surrounding matter and belching jets of radiation into space. This could have been a quasar-like eruption, a cataclysmic feast lasting millions of years, wherein falling gas and dust spiraled into the black hole's maw, releasing enough energy to punch these bubbles through the galaxy's gas and magnetic fields. The bubbles' sharp edges suggest the eruption was swift and violent, like a cosmic champagne cork popping, a single, explosive event rather than a slow leak. But there's another compelling theory. The bubbles might be the work of not one but many generations of stars. The galactic center is a crowded metropolis, home to some of the most massive stars in the Milky Way. When these stars die in supernova, their combined shockwaves could funnel energy outward, sculpting the bubbles over eons. Or perhaps it's a mix of both black hole activity and stellar winds working in concert, their combined energy inflating these gigantic structures like cosmic hot air balloons. The real enigma is why we're only seeing them now. The bubbles are relatively recent discoveries because gamma rays, unlike visible light, pass through dust and gas unimpeded, meaning they've likely been there for millions, if not billions of years, silently towering over us. Their faint glow suggests the eruption that created them has long since subsided, leaving behind a fading echo of a more turbulent time in our galaxy's history. Yet even in their quiet state, they're a reminder that the Milky Way isn't the serene spiral we often picture. Like a dormant volcano, its core has the potential to wake with unimaginable ferocity. What's even more intriguing is what the Fermi Bubbles might be hiding. Some researchers speculate they could be lined with dark matter, their gamma-ray emissions the result of invisible particles colliding and annihilating at their edges. Others suggest they're filled with cosmic rays, high-energy protons, and atomic nuclei accelerated to near-light speeds by the black hole's outbursts. If true, the bubbles could be shaping the very environment of our galaxy, influencing how stars form and how gas circulates between the disk and the halo. One thing's certain, the Fermi Bubbles are a testament to the dynamic, ever-changing nature of galaxies. They force us to confront the idea that even familiar cosmic landscapes can hold surprises, that what seems static might be the aftermath of a forgotten storm. And as we continue to study them, we're left with a humbling thought. If structures this enormous could go unnoticed for so long, what other wonders might be lurking just beyond the edge of our perception? Amid the darkness of intergalactic space, vast clouds of hydrogen gas glow with an eerie, ethereal light, some stretching wider than entire galaxies. These are the Lyman-Alpha Blobs, some of the most mystifying structures in the cosmos, colossal and luminous enough to be seen across billions of light years yet still shrouded in mystery. Named for the specific wavelength of light they emit, Lyman-alpha radiation, these blobs are like cosmic lanterns, their faint but unmistakable glow painting the universe with an otherworldly hue. But what could possibly energize hydrogen clouds on such an unimaginable scale? At first glance, these blobs resemble something out of science fiction, amorphous, glowing behemoths floating in the void. Some span hundreds of thousands of light years, dwarfing even the largest galaxies. The sheer energy required to make them shine so brightly defies easy explanation. One leading theory points to frantic bursts of star formation within the clouds, where thousands of stars ignite at once. their ultraviolet radiation exciting the surrounding hydrogen gas like a neon sign powered by a celestial switchboard. Yet even this staggering stellar activity might not be enough to account for the luminosity of the largest blobs. Then there's the black hole hypothesis. Many Lyman-Alpha Blobs sit at the hearts of young, chaotic galaxies, where supermassive black holes feast on swirling disks of gas and dust. These active galactic nuclei, quasars in their most violent phases, could be pumping out torrents of energy, their radiation heating the surrounding hydrogen until it glows like a cosmic aurora. Some blobs even show signs of colossal outflows, jets of material screaming away from the galactic center at nearly the speed of light, as if the black hole itself is breathing fire into the void. But perhaps the strangest possibility is that these blobs are cosmic fossils, relics from a time when the universe was still in its infancy. In the early cosmos, vast reservoirs of hydrogen gas were common, illuminated by the first generation of stars and galaxies. Some blobs might be leftovers from this epoch, their glow a faint echo of a time when the universe was still stitching itself together. If true, they could be time capsules holding clues to how the first structures formed in the darkness after the Big Bang. Adding another layer to the mystery is the way these blobs cluster. They're often found in the densest regions of space, where galaxies gather in sprawling superclusters, as if the blobs are marking the intersections of cosmic highways. Some researchers think they could be the birthplaces of future galaxy clusters, their hydrogen gas slowly cooling and collapsing to form new stars and worlds over billions of years. Others speculate they might be the aftermath of galactic collisions, where shock waves from crashing galaxies heat the surrounding gas to the point of glowing. The truth is, no single theory fully explains the diversity of Lyman-Alpha Blobs. Some shine steadily, others flicker like distant embers, and a few even pulse with irregular brightness, as if something unseen is stirring inside them. This variability suggests that multiple forces, star formation, black hole activity, even exotic phenomena we haven't yet discovered might be at play, each leaving its own fingerprint on these cosmic clouds. Studying them is like trying to decipher a message written in a language we're only beginning to understand. Every new observation peels back another layer, revealing just how complex and dynamic these structures truly are. And as we piece together their secrets, one thing becomes clear. The universe doesn't just build galaxies and stars, it crafts wonders in the spaces between, painting the darkness with light in ways we're still struggling to comprehend. The Lyman-Alpha Blobs are a reminder that even the emptiest corners of space can hold the most astonishing surprises. Stretching across an almost inconceivable 1.4 billion light-years, the Sloan Great Wall is a galactic titan, a filament of galaxies so vast it makes even the Hercules-Corona Borealis Great Wall seem modest by comparison. Discovered in 2003 by the Sloan Digital Sky Survey, this cosmic leviathan weaves through the constellations of Serpens and Hercules like a bridge between worlds, connecting over 10,000 galaxies in a structure that shouldn't exist according to our most fundamental theories. Imagine a river of stars so wide that if you stood at one end, the other would be lost to the curvature of spacetime itself, a monument to the universe's flair for the grandiose. What makes the Sloan Great Wall so baffling isn't just its size, it's the way it defies the cosmological principle, the idea that matter should be spread evenly across the universe on the largest scales. After the Big Bang, the infant cosmos was thought to be a seething, frothing soup of particles, with tiny fluctuations in density eventually collapsing under gravity to form galaxies and clusters. But structures like this, they stretch the limits of that narrative. The Sloan Great Wall isn't just a cluster or a supercluster, it's a hypercluster, a thread in the cosmic web so dense and elongated that it challenges our understanding of how matter clumped together in the universe's early years. To put its scale into perspective, if our Milky Way were the size of a coffee bean, the Sloan Great Wall would span the length of the continental United States. And here's the kicker, it's not alone. The universe seems to revel in crafting these impossible architectures, the CFA2 Great Wall, the Laniakea Supercluster, and others, each one nudging the boundary of what we thought was cosmologically possible. The Sloan Great Wall, though, stands out for its sheer coherence, its galaxies aligned like pearls on a string, as if the universe decided to sketch a straight line across the void just to remind us how little we truly know. How could such a structure form? One possibility lies in dark matter, the invisible scaffolding of the cosmos. Billions of years ago, dark matter's gravitational pull might have funneled gas and galaxies into these vast filaments, creating highways of matter that stretch across the universe. Another theory suggests the wall is a relic of primordial sound waves density oscillations from the Big Bang that froze into the fabric of space as it expanded, leaving behind echoes in the distribution of galaxies. But even these explanations feel incomplete, like trying to describe a thunderstorm by only talking about the wind. Then there's the unsettling implication. If the Sloan Great Wall exists, what else is out there? Telescopes grow more powerful every year, and with each upgrade we discover structures that push the boundaries of the plausible. Some scientists whisper about the huge large quasar group, a collection of quasars spanning 4 billion light-years, or the South Pole Wall, a curtain of galaxies 500 million light-years long. Each discovery chips away at the notion that the universe is uniform, hinting instead at a cosmos far lumpier and more complex than we ever imagined. The Sloan Great Wall isn't just a curiosity, it's a cosmic rebellion, a silent protest against tidy models and comfortable assumptions. It asks us to reconsider the forces that shaped the universe, to question whether the Big Bang's aftermath was as orderly as we've been taught. And as we stare deeper into the abyss, one thing becomes clear: the universe doesn't just build galaxies, it builds wonders. At the heart of the Phoenix Cluster, a sprawling metropolis of galaxies over 5 billion light-years away, lurks a black hole of almost incomprehensible hunger, one so massive, so ravenous, it's rewriting the rules of how we think these cosmic monsters grow. Clocking in at around 20 billion times the mass of our Sun, this behemoth isn't just the largest black hole known in the universe today. It's a cosmic paradox, a glutton feasting at a rate that defies every model astrophysicists have built. Most supermassive black holes sip on gas and stars like slow sips of coffee, their growth limited by the very heat and radiation their meals produce. But the Phoenix Cluster's black hole, it's gulping down matter like there's no tomorrow, consuming the equivalent of 60 Earths worth of material every single day. What makes this feeding frenzy even more astonishing is what happens to the leftovers. As gas spirals into the black hole's maw, some of it gets blasted back out in twin jets of charged particles, shooting away at nearly the speed of light. These jets punch through the surrounding galaxy cluster, heating the gas between galaxies to temperatures surpassing trillions of degrees, so hot that even protons and neutrons begin to break apart. Normally, black hole jets act like cosmic pressure valves, their energy preventing too much gas from cooling and falling inward. But here, the system's gone haywire. Instead of regulating itself, the black hole's output is so extreme it's become a runaway train, superheating the cluster's gas to the point where it glows brighter in X-rays than any other known cluster in the universe. The Phoenix Cluster wasn't always this violent. Observations suggest it was once a quiet, cool core cluster where gas gradually cooled to form new stars until something tipped the scales. One theory is that a galactic collision funneled an unusually dense river of gas toward the black hole, igniting a feedback loop of gluttony and fury. The more it ate, the more energy it released, but instead of stifling its appetite, the heat might have stirred the gas into a frothy, turbulent state, making it even easier for the black hole to keep feeding. It's like trying to put out a fire with gasoline. Every attempt to stabilize the system only makes it more volatile. But the real mystery lies in how this black hole got so big in the first place. According to conventional models, black holes this massive should take tens of billions of years to form, yet the universe itself is only 13.8 billion years old. Did it start as a rare seed black hole from the early cosmos, born already thousands of times the Sun's mass? Or did it grow through some exotic mechanism we haven't yet discovered, like feasting on dark matter or merging with other black holes in a way that bypassed the usual limits? The Phoenix Cluster's central monster challenges the very timeline of how cosmic structures evolve, forcing us to reconsider what's possible in the chaos of the universe's most extreme environments. Then there's the fallout. The black hole's jets aren't just heating gas, they're sculpting it, carving enormous cavities in the cluster that span hundreds of thousands of light years. These bubbles, visible in radio waves, are like fingerprints of the black hole's fury, proof of the titanic forces at play. Even more bizarre, the jets seem to be triggering star formation in some regions while stifling it in others, their energy both nurturing and devastating the cosmic landscape in equal measure. It's as if the black hole is playing the role of chaotic gardener, sowing stars with one hand while uprooting them with the other. The Phoenix Cluster's black hole is more than just a record breaker, it's a cosmic lesson in extremes. It shows us that black holes aren't just passive drains in space-time but dynamic, chaotic engines capable of reshaping entire clusters. And as we study its violent tantrums, we're left with a humbling thought. If this is what a black hole can do when the rules break down, what other surprises might be lurking in the depths of the cosmos? Tucked away in the cosmic microwave background, the faint afterglow of the Big Bang, there's a patch of sky that doesn't belong. Known as the cold spot, this region in the constellation Eridanus is noticeably colder than its surroundings, a cosmic anomaly stretching over 1.8 billion light years. At first glance, it might seem like a trivial fluctuation, a statistical hiccup in the universe's thermal fingerprint. But this chill runs deep, sparking debates that cut to the very core of cosmology. Is it a meaningless outlier, or could it be evidence of something far stranger, a crack in reality itself? When the cold spot was first detected by NASA's Wilkinson Microwave Anisotropy Probe in 2004, astronomers assumed it was just noise, a random cold patch in the otherwise uniform haze of the CMB. But as more precise measurements rolled in from missions like the Planck satellite, the anomaly refused to vanish. The temperature difference is slight, just 70 microkelvins colder than average, but the scale is staggering. A region this large and this cold shouldn't exist under standard cosmological models, which predict that the early universe's temperature variations should be far more evenly distributed. The odds of such a fluke appearing by chance, less than 1 in 50. So what could explain it? One possibility is that we're staring at a supervoid, an enormous, nearly empty region of space where the lack of matter subtly cools the CMB photons passing through it. It's like watching light filter through a frosted window. The void's underdensity might stretch the photons' wavelength slightly, making them appear colder. But here's the catch. Surveys of the cold spot's vicinity haven't found a void large or deep enough to account for the temperature drop. The universe's largest known voids are still too small by a factor of 10, leaving this explanation on shaky ground. Then there's the far more radical idea. The cold spot might be a cosmic bruise, a remnant of a collision with another universe. In the multiverse theory, our universe could be one bubble in an endless froth of realities, each with its own physical laws. If another bubble universe grazed ours in the distant past, the energy released at the boundary could have left behind a cold imprint, like a fingerprint smudged onto the fabric of space-time. It's a fringe hypothesis, but one that's impossible to ignore when staring down an anomaly of this magnitude. But perhaps the most mind-bending explanation is that the cold spot is a cosmic texture, a topological defect in space-time left over from the universe's violent birth. In the first fractions of a second after the Big Bang, the fundamental forces of nature were still merging and splitting, their symmetries breaking like ice cracking under pressure. These phase transitions could have created imperfections in spacetime itself, knots of energy that, when they unraveled, released shockwaves of gravity powerful enough to leave a cold scar on the CMB. If true, the cold spot wouldn't just be a curiosity, it'd be a fossil of the universe's most primordial moments, a relic from a time before time. The challenge is that each of these theories comes with its own set of contradictions. Supervoids struggle to explain the scale, multiverse collisions border on untestable speculation, and cosmic textures remain purely theoretical. Yet the cold spot refuses to be dismissed, its chill lingering like a whisper from the cosmos. Future telescopes like the Simons Observatory or CMBS-4 may finally settle the debate, peering deeper into this enigmatic region with unprecedented sensitivity. What makes the cold spot so compelling isn't just the science, it's the reminder that even our most refined models of the universe are provisional. Here's a structure that defies categorization, a mystery that could rewrite textbooks or fade into statistical obscurity. But until we know for sure, it stands as a beacon of the unknown, a cold splash of uncertainty in our otherwise warm and orderly cosmic narrative. Arranged across the distant constellations of Boötes and Draco like a celestial smile, the giant arc is a structure so vast it rewrites our understanding of cosmic architecture. Stretching an astonishing 3.3 billion light-years across, this nearly perfect crescent of galaxies was discovered in 2021, and it's turning cosmology on its head. Picture a bowstring drawn taut against the darkness, connecting dozens of galaxy clusters in a graceful curve so immense that if you could see it with the naked eye, it would span the width of 20 full moons in our sky. But here's what makes it truly extraordinary. According to everything we know about the universe's large-scale structure, something this big and this symmetrical simply shouldn't exist. The cosmological principle, one of astronomy's foundational ideas, states that on the grandest scales, the universe should appear roughly uniform, no matter where you look. Matter ought to be sprinkled evenly, like flour sifted through a cosmic sieve. Yet the giant arc flouts this rule with brazen elegance. Its galaxies aren't scattered randomly, they're aligned along a curve with striking coherence, as if some unseen hand sketched a parenthesis across the cosmos. For scale, this structure is so lengthy that light leaving one end when the universe was just half its current age would only now be arriving at the other. That's not just a challenge to theories, it's a cosmic provocation. So how did such a behemoth form? One clue lies in its composition. The arc isn't a solid wall but a filament, a thread in the cosmic web where galaxies cluster like beads on a string. These filaments typically span hundreds of millions of light-years, but the giant arc dwarfs them all, stretching far beyond what gravity alone should permit in a 13.8 billion-year-old universe. Some theorists suggest it might be a relic of primordial sound waves, ripples from the Big Bang that froze into the distribution of matter as space expanded. Others wonder if we're seeing the imprint of dark matter's hidden scaffolding, its gravitational pull orchestrating galaxies into this improbable alignment over eons. But there's a catch: the arc's symmetry. Natural structures this vast tend to be messy, warped by the chaotic dance of gravity over billions of years. The giant arc, by contrast, maintains a curvature so precise it feels almost designed. Could this be evidence of exotic physics, a domain where dark energy's repulsive force sculpts matter into unexpected shapes? Or might it hint that the early universe was far less uniform than we've assumed, with density variations powerful enough to birth such anomalies? The discovery has sent shockwaves through astronomy because it's not just an outlier, it's part of a pattern. From the Hercules-Corona Borealis Great Wall to the Sloan Great Wall, each new mammoth structure chips away at the cosmological principle, suggesting the universe might be more lumpy than our models allow. If these titans are real, they could upend our understanding of cosmic inflation. the process that supposedly smoothed the infant universe into homogeneity. What's exhilarating is that the giant arc isn't some ancient relic frozen in time. The galaxies within it are evolving, colliding, birthing stars, a living, breathing monument to the universe's unyielding creativity. And as telescopes grow sharper, we might find even grander structures, each one a puzzle piece in the question we've asked since the dawn of civilization. How exactly does the cosmos organize itself? For now, the giant arc stands as both a masterpiece and a riddle, a reminder that the universe's blueprints are far stranger than we ever dreamed. Out in the constellation Monoceros, 1,200 light-years from Earth, the Red Rectangle Nebula floats like a stained glass window left ajar in the cosmos, its sharp, geometric edges slicing through the surrounding chaos with eerie precision. Most nebulae are billowing clouds of gas, twisted and turbulent, shaped by the whims of stellar winds and explosions. But this one, it's a cosmic anomaly, a near-perfect X carved from dust and glowing hydrogen, its symmetry so startling it looks almost engineered. How does nature, with its love of asymmetry and randomness, craft something so meticulously angular? The answer might lie in the heart of the nebula, where two stars dance in a gravitational embrace, orchestrating this celestial artistry. At the center of the Red Rectangle, a binary star system known as HD 44179 spins in a tight 15.8-year orbit. One of these stars is a red giant, bloated and aging, shedding its outer layers in a slow-motion death spiral. The other, a smaller companion, funnels this expelled material into twin cones of dust and gas, their opposing jets colliding and flattening into the nebula's distinctive hourglass shape. From our vantage point, that hourglass appears as an X, a trick of perspective, as we're peering almost directly down the barrel of one cone while the other fans outward. What's mesmerizing is how clean the lines are. Unlike the ragged edges of most nebulae, the Red Rectangle's borders are crisp, its geometry preserved by the stability of the binary system's orbit. It's as if the stars are working in tandem, one feeding the other, their gravitational choreography sculpting the surrounding chaos into order. But here's the real puzzle: why isn't this symmetry more common? Binary stars are everywhere in the universe, yet almost none of their nebulae exhibit this level of precision. The Red Rectangle's secret might lie in its rare alignment, a perfect storm of factors that let the cones form without disruption. The red giant's mass loss is slow and steady, unlike the violent eruptions of younger stars, allowing the dust to settle into neat layers. The companion star's orbit is just wide enough to avoid turbulence but close enough to focus the outflow. Even the nebula's nickname is a misnomer. High-resolution images reveal its rectangle is more of a ladder, with rungs of dust connecting the cones like scaffolding. This intricate structure suggests the system has been undisturbed for millennia, a cosmic still life untouched by passing shocks or collisions. Then there's the color, a deep, rusty red that gives the nebula its name. This hue comes from a class of organic molecules called polycyclic aromatic hydrocarbons, or PAH, which glow when bombarded by ultraviolet light from the central stars. These molecules are common in space, but in the Red Rectangle, they're arranged in a way that amplifies their emission, creating that rich, brick-like tone. Some scientists speculate the nebula could even be a factory for complex carbon compounds, its dense dust lanes acting as a laboratory for probiotic chemistry. If true, this geometric marvel might not just be a cosmic oddity, it could be a cradle for the building blocks of life. But time is running out. The red giant at the nebula's heart is nearing the end of its life, destined to shrink into a white dwarf in the astronomical blink of an eye. When that happens, its stellar winds will weaken, and the nebula's delicate structure will unravel, its dust dissipating into the void. For now, though, the Red Rectangle stands as a fleeting masterpiece, a reminder that even in the chaos of the cosmos, there are moments of perfect balance where gravity and light conspire to create something inexplicably beautiful. And in its fleeting symmetry, it whispers a question. How many other geometric wonders are hiding in the darkness, waiting to be found? Hidden in the swirling arms of the galaxy NGC 4258, a cosmic whisper echoes through the void, not in light or radio waves, but in the faint, rhythmic pulse of water molecules. This is a megamesa galaxy, where vast clouds of water vapor amplify microwave radiation into beams so intense they shine like interstellar lighthouses. But what makes this distant spiral special isn't just its natural lasers, it's the way these masers have turned its supermassive black hole into a laboratory for testing the very fabric of spacetime. At the galaxy's heart, a black hole weighing 40 million suns spins, its gravity warping the surrounding disk of gas into a frenzied whirlpool. Normally, such disks are chaotic and turbulent, their structures too blurry to map with precision. But here, something extraordinary happens. The water molecules in the disk's outer layers absorb energy from the black hole's radiation, then re-emit it as coherent microwave beams, masers, that act like cosmic rulers, marking the disk's structure with pinpoint accuracy. It's as if the universe handed astronomers a finely etched blueprint of a black hole's domain, a chance to study Einstein's general relativity in action. And what they've found is breathtaking. By tracking the motion of these masers, scientists have mapped the disk's rotation with unprecedented detail, watching as gas spirals inward at hundreds of kilometers per second. The results match Einstein's predictions with eerie precision. The inner orbits tilt and twist like a spinning top under the black hole's gravitational pull, space itself dragged into a vortex around the monster's maw. This isn't just theory anymore, it's direct observation, a confirmation that even in the most extreme environments, relativity holds sway. Yet the masers reveal more than just textbook physics. They've exposed a mystery. The disk is warped, its outer layers bent at a sharp angle to the black hole's spin. Some suspect a past galactic collision where another black hole or stray star cluster plowed through the disk, leaving it permanently crooked. Others think the warp might be fueled by magnetic fields, their invisible lines of force twisting the gas like taffy. Whatever the cause, this kink is a cosmic gift, a natural experiment showing how black holes feed, how their disks evolve, and how even the mightiest structures in the universe can be sculpted by unseen forces. What's truly remarkable is how lucky we are to see this at all. Masers like these are rare, requiring just the right mix of water density, temperature, and energy to ignite. That NGC 4258's disk aligns so perfectly with our line of sight, allowing the maser beams to shine straight at us is a stroke of cosmic serendipity. Without it, we'd never have glimpsed the intricate dance of matter and gravity at this resolution, or tested relativity with such clarity. So while megamasers might sound like an obscure footnote in astronomy, they're anything but. They're nature's precision tools, carving pathways through the noise of the universe to reveal its deepest secrets. And in the twisted disk of NGC 4258, they've given us something even rarer, a front-row seat to the silent, swirling ballet of spacetime itself. In the vast expanse of the cosmos, where galaxies cluster like bustling cities and superclusters weave the grand tapestry of the universe, there's a region so eerily underpopulated it feels like a cosmic oversight. This is the so-called empty quadrant, an expanse of sky where galaxies appear suspiciously sparse, a void stretching across a section of the universe so vast it beggars belief. Unlike the Boots void, which at least hosts a smattering of lonely galaxies, this quadrant seems almost barren, a desert of darkness where the usual celestial landmarks simply aren't. At first glance, you might dismiss it as a statistical fluke. After all, the universe is unimaginably large, and randomness ensures some regions will appear emptier than others. But when astronomers first mapped this quadrant, the scarcity of galaxies wasn't just notable, it was statistically jarring. Surveys that should have revealed thousands of galaxies instead turned up mere hundreds, as though some unseen hand had swept through the cosmos with a broom, clearing the celestial floor. The odds of such a gap occurring naturally, astronomers calculate them at less than 1 in 1,000. So what's really going on here? One possibility is that we're staring into an observational blind spot, a region where interstellar dust or some other cosmic curtain blocks our view. Our own Milky Way's galactic plane creates a similar effect, the zone of avoidance, where dust and stars obscure the universe beyond. But this quadrant lies far from the Milky Way's obscuring disk, leaving no obvious local culprit for the missing galaxies. Could it be a vast, undiscovered dust cloud on an intergalactic scale, or is something else at play? Another unsettling theory suggests the quadrant might be a genuine cosmic anomaly, a region where matter, for reasons unknown, failed to cluster as densely as elsewhere. If true, it would challenge the cosmological principle, the bedrock assumption that the universe is homogeneous on large scales. We've already seen hints of this with structures like the giant arc and the Hercules-Corona Borealis Great Wall, but an absence of structure would be even more provocative. It would imply that the universe isn't just uneven in its distribution of matter, but might have fundamental, asymmetric flaws woven into its fabric. Then there's the most tantalizing possibility that the empty quadrant isn't empty at all. Instead, it could be filled with dark matter, the invisible, ghostly substance that makes up most of the universe's mass. If dark matter clumped differently here, its gravitational pull might have suppressed galaxy formation, leaving behind a shadowy realm where normal matter never coalesced into stars and galaxies. We'd be staring at a cosmic mirage, a place that looks barren but is actually teeming with the unseen. What's fascinating is how this quadrant forces us to question our tools as much as our theories. Could our telescopes and surveys simply be missing faint, distant galaxies in this region? Or are we seeing the limits of our current technology, where the dimmest structures blur into the background noise of the universe? Future observatories, like the James Webb Space Telescope's successors, might finally shed light on this enigma, either revealing hidden galaxies or confirming that we've stumbled upon one of the cosmos' most profound irregularities. For now, the empty quadrant remains a puzzle, a silent challenge to our understanding of how the universe arranges itself. Whether it's a trick of perspective, a dark matter stronghold, or a genuine cosmic anomaly, one thing's certain: the universe doesn't do anything without a reason. And in this vast stretch of apparent nothingness, that reason might just rewrite the rules. Imagine a world where diamonds aren't rare gems but the very ground beneath your feet, a planet so dense, so unimaginably wealthy in crystallized carbon that it makes Earth's deepest mines look like sandboxes. Meet PSR J 1719-1438b, a cosmic jewel orbiting a pulsar 1,000 light-years away, a place where the universe flexes its flair for the extreme. This isn't just any exoplanet, it's the remnants of a once mighty star, crushed into a diamond the size of Jupiter, spinning around a stellar corpse at breakneck speeds. The story begins with its host, a millisecond pulsar, a neutron star spinning hundreds of times per second, its beams of radiation slicing through space like a lighthouse gone rogue. Pulsars like this often have violent histories, and this one's no exception. Astronomers believe it once had a companion star, a white dwarf that orbited too close. Over eons, the pulsar's gravity siphoned away the dwarf's outer layers, leaving behind a core so compressed that its carbon crystallized into a planet-sized diamond. The result, a world where the very atoms are packed so tightly they've hardened into a lattice of gemstone, a sphere of crystalline carbon forged under pressures we can't replicate anywhere in the solar system. What's even more astonishing is the speed of this cosmic dance. PSR J 1719-1438b completes an orbit in just 2 hours and 10 minutes, hurtling around its pulsar at nearly 500,000 miles per hour. At that velocity, a year here passes in less time than it takes to watch a movie. The gravitational forces at play are so intense that if you could stand on this planet's surface, though you'd be crushed instantly, the sky would be a blinding strobe of pulsar radiation, the horizon bending under the weight of its own density. But here's the real puzzle. Could such a world harbor something even stranger than diamond? Some theorists speculate that under these extreme conditions, carbon might morph into exotic states of matter, perhaps a form of superconducting crystal or even carbon metallic hydrogen, a hypothetical phase where hydrogen atoms bond with carbon in ways impossible under Earth-like pressures. Others wonder if the planet's core might host quantum phenomena we've never observed, where electrons flow without resistance or where the lines between solid and liquid blur into something entirely new. The irony is that PSRJ 1719-1438b might be both priceless and worthless. Its diamond composition is a celestial marvel, but the forces required to mine it, let alone reach it, are beyond any conceivable technology. And yet, its existence expands the realm of what's possible. If a diamond planet can form around a pulsar, what other absurdly exotic worlds might be hiding in the cosmos? Could there be planets made of pure iron or oceans of liquid metallic hydrogen? This pulsar-orbiting gem challenges our definitions of a planet itself. It's not a rocky world like Earth or a gas giant like Jupiter. It's a relic of stellar cannibalism, a monument to the universe's ability to transform catastrophe into beauty. And as we stare at its flickering light, we're left with a tantalizing thought. In a cosmos where diamonds rain from the skies of Neptune and planets orbit dead stars, the line between science and science fiction has never been thinner. Nestled in the heart of the Perseus cluster, 220 million light-years from Earth, lurks a cosmic anachronism, NGC 1277, a galaxy that refused to grow up. While other galaxies spent the last 10 billion years merging, birthing stars, and evolving into the grand spirals and ellipticals we know today, this relic of the early universe simply stopped. It's a fossil frozen in time, a celestial snapshot of what galaxies looked like when the cosmos was barely a third of its current age. But what makes NGC 1277 truly bizarre isn't just its arrested development, it's what's missing. This ancient behemoth, packed with twice as many stars as our Milky Way, appears to harbor almost no dark matter, the invisible glue that holds galaxies together. How could something so massive defy one of cosmology's most fundamental rules? The galaxy's story begins in the universe's chaotic youth, when galaxies formed in a frenzy of collisions and star formation. NGC 1277 was a champion in this era, ballooning to its enormous size through a series of violent mergers before abruptly shutting down. Unlike typical galaxies, which continuously recycle gas into new stars, this one exhausted its fuel reserves early, leaving it full of aging red stars and devoid of the blue sparkle of stellar nurseries. It's as if the galaxy burned through its cosmic inheritance in a wild spree and then retreated into isolation, a hermit clinging to the remnants of its glory days. Yet the real shock came when astronomers tried to weigh it. Galaxies this massive usually owe their heft to dark matter, the invisible substance that makes up 85% of the universe's mass. Its gravitational pull should keep stars orbiting at specific speeds, but in NGC 1277, the stars move far slower than expected, as if the galaxy's gravity comes solely from the stars themselves. It's like watching a car race where one vehicle speeds around the track without an engine. Something's clearly off. One theory suggests the galaxy might have been stripped of its dark matter during a close encounter with the Perseus cluster's turbulent core, where gravitational tides could have ripped the invisible halo away. Another possibility is even stranger, that NGC 1277 formed in a rare region of the early universe where dark matter was unusually sparse, making it a cosmic contrarian from birth. What's tantalizing is how this galactic time capsule challenges our models of galaxy evolution. If dark matter isn't always the anchor we thought, could there be other outliers like this lurking in the shadows? Or is NGC 1277 a fluke, a cosmic mutation that survived against all odds? Every observation peels back another layer, revealing a universe far more unpredictable than our textbooks suggest. And in its stubborn refusal to conform, this cannibal galaxy holds up a mirror to the past, showing us just how much we still have to learn about the forces that sculpt the cosmos. In the quiet static of radio telescopes, astronomers stumbled upon something that shouldn't exist: massive rings of energy floating in the cosmic darkness, so large they could swallow entire galaxies whole. These are odd radio circles, or mysterious, ghostly structures detected only in radio waves, invisible to every other part of the electromagnetic spectrum. Picture ripples on a pond, but scaled up to cosmic proportions, perfect circles stretching nearly 1,000,000 light-years across, their origins shrouded in enigma. Discovered just a few years ago, they've already upended expectations, leaving scientists scrambling to explain how such flawless, gargantuan rings could form without leaving a trace in visible light, X-rays, or any other wavelength we can detect. The first clue to their nature lies in what they're not. ORCs aren't supernova remnants. Those chaotic, twisted clouds of debris are far messier. They're not planetary nebulas either, the delicate shells cast off by dying stars. And they're certainly not Einstein rings, those graceful distortions of light caused by gravitational lensing. No, ORCs are something else entirely, symmetrical, isolated, and eerily uniform, like cosmic smoke rings blown by an unseen giant. When researchers first spotted them in data from Australia's ASCAP radio telescope, the assumption was that they had to be some kind of instrument glitch, but as more circles emerged across the sky, the truth became unavoidable. The universe had been hiding these colossal rings in plain sight, and we'd somehow missed them until now. So what could possibly create such bizarre structures? One leading theory points to shock waves from cataclysmic galactic collisions. When two galaxies merge, the resulting explosion of energy can send out spherical waves of gas and plasma, like the blast from a stellar megabomb. If these waves propagate evenly, they might carve out the perfect circles we see as ORCs. The problem: most galactic collisions leave behind telltale evidence, distorted shapes, bursts of star formation, or glowing X-ray halos, and ORCs show none of that. They're pristine, as if whatever formed them erased all other traces of the violence that birthed them. Then there's the black hole hypothesis. Supermassive black holes at the centers of galaxies are known to belch out enormous jets of material when they feed, but those jets are typically narrow and focused, not broad, symmetrical rings. Unless, of course, the black hole had a meal so colossal that it triggered a spherical eruption, a kind of cosmic burp rippling outward in all directions. Some simulations suggest this could happen if a black hole devoured an entire galaxy's worth of gas at once, releasing enough energy to inflate a bubble of radio-emitting particles. But even this explanation feels incomplete. Why don't we see the aftermath of such a feast? Where are the glowing remnants of the devoured material? Perhaps the most tantalizing idea is that ORCs are something entirely new, a previously unknown phenomenon, a cosmic process we haven't even begun to theorize about. They might be the fingerprints of dark matter interactions, or the echoes of primordial quantum fluctuations frozen in space-time. Some have even speculated they could be throat clearings from advanced civilizations, though that's firmly in the realm of science fiction. What makes ORCs so thrilling is their refusal to fit neatly into any box. They're cosmic outliers, challenging us to rethink what we know about how energy and matter behave on the largest scales. And here's the twist: ORCs might not even be rare. Early surveys suggest they could number in the thousands across the sky, hidden until now by the limitations of our technology. As radio telescopes grow more sensitive, we're likely to find more of these enigmatic rings, each one a fresh puzzle waiting to be solved. For now, they hover at the edge of our understanding, silent and unexplained, a reminder that the universe still has cards it hasn't shown us. And in their perfect radio wave silence, they ask the most tantalizing question of all: what else are we missing? Out in the constellation Cetus, 260 million light-years from Earth, a galaxy hangs like a ghost in the void. NGC 1052DF2, a cosmic rebel that defies one of astronomy's most fundamental beliefs. This wispy, translucent galaxy, barely visible against the blackness of space, holds a secret that sent shockwaves through cosmology. It appears to have no dark matter at all. That's like finding a towering skyscraper with no steel framework, a structure standing tall against gravity without the very thing thought to hold it together. For decades, dark matter has been the invisible hand shaping the universe, its gravitational pull explaining why galaxies spin faster than their visible mass should allow. Yet here's NGC 1052DF2 spinning lazily as if the rules don't apply. The discovery sent astronomers scrambling. How could a galaxy this large, roughly the size of the Milky Way but with only 1% of its stars, exist without dark matter's gravitational anchor? Initial measurements showed its stars moving at a sluggish pace, their velocities too slow to require any unseen mass. It was as if someone had taken a standard galaxy and stripped out the dark matter, leaving behind a fragile skeleton of stars and gas. Skeptics argued it must be a measurement error, a trick of perspective, but follow-up studies only deepened the mystery. The galaxy's globular clusters, dense groups of ancient stars orbiting its core, also moved sluggishly, confirming the absence of dark matter's telltale gravitational grip. This left scientists with two equally unsettling possibilities. Either NGC 1052DF2 disproves the dark matter hypothesis entirely, suggesting galaxies can form without it, or dark matter isn't as universally distributed as we thought. The first option would upend decades of cosmology, forcing us to reconsider everything from galaxy formation to the very fabric of gravity itself. The second, however, might be even stranger. Perhaps the galaxy's dark matter was violently stripped away by a past collision, leaving it bizarrely hollow. Or maybe it formed in a rare pocket of the universe where dark matter was inexplicably sparse, a cosmic fluke birthed in unusual conditions. Adding fuel to the fire, astronomers soon found another dark matter-deficient galaxy nearby, NGC 1052DF4, as if the universe was doubling down on the challenge. Together, these outliers force us to confront uncomfortable questions. Are they statistical oddities or evidence of a broader phenomenon we've overlooked? Could dark matter interact with itself in ways that occasionally push it out of galaxies? Or is there some exotic process, a dark matter wind or an unseen force, that can scour it clean from certain regions of space? What's fascinating is how these galaxies refuse to fit neatly into any box. They're not just curiosities, they're stress tests for our theories, pushing the limits of what we think we know. If dark matter is as ubiquitous as we believe, why do these exceptions exist? And if they're more common than we realize, what does that mean for our models of the universe's structure? Every observation peels back another layer, revealing a cosmos far more nuanced than our textbooks suggest. NGC 1052DF2 isn't just a galactic oddball, it's a cosmic provocateur, daring us to rethink the invisible scaffolding of reality itself. Far beyond the orbit of Neptune, where sunlight dwindles to a faint memory, a tiny world named the Goblin drifts along an orbit so stretched it defies belief. This icy dwarf planet, officially designated 2015 TG 387, takes 40,000 years to complete a single trip around the Sun, spending most of that time in the solar system's frozen badlands, nearly 2,000 times farther out than Earth. But what makes the Goblin truly fascinating isn't just its lonely journey, it's the way its path acts like a celestial compass, pointing towards something much larger lurking in the darkness, the hypothetical planet 9. The Goblin's orbit is no random accident. Like several other extreme trans-Neptunian objects, it follows a peculiar clustering pattern. Its elongated path aligned with similar distant worlds in a way that suggests an unseen hand is guiding them. Picture a series of comets scattered across a table. If you nudge them with a hidden magnet, their paths would naturally align in a similar direction. That's precisely what astronomers think might be happening here. The gravitational influence of a massive, undiscovered planet, Planet 9, could be herding these distant objects into their strange, synchronized orbits. The math behind this theory is compelling. Simulations show that a planet roughly 5 to 10 times Earth's mass, orbiting hundreds of times farther out than we do, would neatly explain the Goblin's trajectory, along with the odd paths of its kin like Sedna and 2012 VP-113. Without Planet 9's gravitational pull, these objects should be randomly oriented like leaves scattering in the wind. Instead, they're all pointing toward the same patch of sky, as if tied to an invisible leash. But the Goblin isn't just a clue, it's a test. Every new extreme object discovered tightens the constraints on where Planet 9 might hide. The Goblin's orbit, for instance, rules out a huge swath of potential locations, narrowing the search like a cosmic game of battleship. And the deeper we look, the stranger the picture becomes. Some models suggest Planet 9 could be a captured rogue planet, stolen from another star system long ago. Others speculate it might be a primordial black hole, its gravity warping space without emitting light. What's thrilling is how much we're learning from these distant messengers. The Goblin's surface, likely coated in exotic ices and organic compounds, is a frozen time capsule from the solar system's birth. Its orbit, sculpted by forces we're only beginning to understand, maps the gravitational contours of our cosmic backyard. And with every new discovery, we're not just hunting for Planet 9, we're rewriting the story of how planetary systems form and what might still be hiding in the dark. The outer solar system, it seems, is far from empty. It's a dynamic frontier where dwarf planets trace the whispers of unseen giants, where the faintest gravitational tugs can reveal worlds we never imagined. And as the Goblin continues its 40-millennium journey, it carries with it a tantalizing promise. The universe always keeps its most thrilling secrets just out of sight, waiting for us to look closer. Hidden in the constellation Monoceros, just 1,500 light-years from Earth, there's a cosmic paradox lurking beside a dying star. The unicorn, one of the smallest black holes ever discovered, defies everything we thought we knew about how these gravitational monsters form. Tipping the scales at just 3 times the mass of our Sun, this tiny titan sits right in the middle of the so-called mass gap, a mysterious no-man's land where black holes weren't supposed to exist. Its very existence throws a wrench into decades of stellar evolution models, forcing astronomers to ask, have we been missing an entire population of hidden black holes all along? What makes the unicorn so perplexing is its size. Conventional wisdom divided compact stellar remnants into neat categories. Neutron stars, those dense city-sized cores left after supernova, capped at around 2.2 solar masses, and black holes, the gravitational abysses born from the collapse of the most massive stars, usually starting at 5 solar masses or more. Between them, a desert, a theoretical dead zone where collapsing stars weren't thought to produce stable remnants. Yet here's the unicorn snugly sitting at 3 solar masses, smack in the middle of that forbidden range. It's like finding a hummingbird-sized elephant, a creature that shouldn't exist by the rules of nature. The discovery hinged on its tortured companion, a dying red giant star caught in a gravitational waltz so tight that the black hole strips away its outer layers, stretching the star into a teardrop shape. By tracking the red giant's rhythmic dimming and velocity shifts, astronomers pieced together the unicorn's presence, an invisible dancer tugging its partner through space. This indirect detection method raises a spine-tingling possibility. What if the cosmos is teeming with similar black holes, quietly orbiting stars without the telltale X-ray glow we typically use to spot them? But how did the unicorn form in the first place? One theory suggests it's the stripped-down core of a massive star that lost its outer layers to a binary companion long ago, collapsing without the fireworks of a traditional supernova. Another posits that neutron stars might occasionally accrete enough material to tip them over the edge into black hole territory, bridging the mass gap in a slow-motion transformation. Then there's the wild card. Could some of these small black holes be primordial, forged not from stars but from the intense pressures of the early universe itself? The implications ripple far beyond this one oddity. If the mass gap isn't a gap at all but a hidden highway of black holes, it could rewrite how we understand stellar life cycles. Supernova models might need recalibrating. Gravitational wave predictions could require adjustments. Even the search for habitable planets gets a twist. What if unseen black holes lurk in seemingly peaceful star systems, their subtle tugs occasionally destabilizing orbits? For now, the unicorn remains a tantalizing outlier, a cosmic whisper hinting at the gaps in our knowledge. But with every new observation, it pushes us closer to a startling realization. The universe doesn't play by tidy rules. And in the shadows between what we know and what we've yet to discover, there might be countless more unicorns waiting to be found. Deep in the constellation Scorpius, a cosmic rebel spins silently in the void. Hess J 1731-347, a neutron star so light it shouldn't exist. Clocking in at just 0.77 times the mass of our Sun, this stellar corpse defies every textbook on compact objects, weighing less than half what physicists thought possible for such a dense remnant. Neutron stars are supposed to be the universe's ultimate pressure cookers, their cores crammed so full of neutrons that a sugar cube-sized chunk would outweigh Mount Everest. Yet here's Hess J 1731-347, barely holding itself together, flirting with the lower edge of stability like a soap bubble on the verge of popping. What makes this neutron star so puzzling isn't just its weight, it's how it survived at all. When massive stars collapse, their cores typically crunch down into neutron stars only if they have enough mass to overcome something called the Tolman-Oppenheimer-Volkoff limit, the point where gravity trumps quantum forces. Anything lighter should fizzle into a white dwarf, while heavier cores collapse into black holes. Hess J 1731-347 sits in a forbidden zone, too light to fit the models yet still packing the density and magnetic fury of a true neutron star. It's like finding a boulder floating in midair, an object that by all known physics should have fallen long ago. This anomaly has led some scientists to propose an even wilder possibility. Maybe it's not a neutron star at all. Perhaps Hess J 1731-347 is something far more exotic, a strange quark star, a hypothetical object where the crushing pressures have shattered neutrons into their fundamental components, a soup of free-floating up, down, and strange quarks. In normal neutron stars, quarks remain locked inside neutrons like prisoners in cells. But under extreme enough conditions, those walls might break, creating a bizarre state of matter where quarks flow freely, unbound by the usual rules. A quark star would be denser than a neutron star, yet paradoxically lighter, a cosmic matryoshka doll hiding a radically different interior. The evidence for this idea comes from Hess J 1731-347's behavior. Its X-ray emissions flicker in ways that don't quite match pure neutron star models, and its surface temperature is oddly cool for its estimated age. If it's a quark star, these quirks might stem from its core radiating energy differently, its quark-gluon plasma behaving like nothing we've ever observed. Even its low mass could fit the theory quark matter might stabilize at lower densities, allowing such lightweight objects to exist without immediately collapsing. But proving this would require rewriting decades of astrophysics. Strange quark stars have never been definitively detected, and their existence hinges on quantum chromodynamics, the notoriously complex theory governing quark interactions. If confirmed, HES J1731-347 wouldn't just be an oddity, it would open a window into the universe's most extreme states of matter, offering clues about how quarks behave when freed from their atomic prisons. This could reshape our understanding of everything from supernova to the early universe's quark-gluon plasma. Yet the mystery deepens when we ask how such a star formed in the first place. Did its progenitor star collapse unusually gently, leaving behind a sparse remnant? Was it born in a binary system where a companion star siphoned away its mass, starving it into this underweight state? Or does its existence hint at entirely new physics, a hidden threshold where neutron stars can form lighter than we ever dreamed? For now, HES J1731-347 remains a tantalizing enigma, a cosmic featherweight punching above its class, challenging us to rethink the boundaries of matter itself. Whether it's a neutron star defying the odds or the first confirmed quark star, one thing's clear: the universe has a habit of crafting exceptions to every rule we write. And in the quiet glow of this impossible object, we're reminded that some of the boldest discoveries begin with a single, stubborn outlier. Streaking through the void at 5 million miles per hour, a cosmic fugitive tears through the darkness, a supermassive black hole, violently ejected from its home galaxy and now racing unchecked through intergalactic space. This isn't some abstract phenomenon. It's a gravitational outlaw, a monster with the mass of 20 million suns caught in the act of escape, and the trail it leaves behind. A shimmering river of newborn stars glowing like breadcrumbs scattered across the cosmos. The story of this runaway begins with a cataclysmic merger. Picture two galaxies, each with its own supermassive black hole anchored at the center, spiraling toward one another in a gravitational tango lasting millions of years. When they finally collide, their black holes sink toward the newly formed galactic core, whirling around each other in a tightening orbit. But here's where physics gets chaotic. As they spin, they emit ripples in space-time gravitational waves that carry away energy, pushing them closer. If their final approach isn't perfectly balanced, the recoil from these waves can fling one of the black holes away like a slingshot, sending it careening into the abyss. That's likely what happened here, a three-body dance gone wrong where the interloper got tossed out with enough force to escape its galaxy's grip entirely. What's astonishing isn't just the black hole's speed, it's the aftermath. As it plows through the thin gas between galaxies, its gravitational pull compresses the material in its wake, triggering bursts of star formation. Imagine a ship cutting through ocean waves, leaving a churning wake behind it, except here, the waves are clouds of gas collapsing into young blue stars. This celestial contrail stretches tens of thousands of light years, a glowing scar marking the black hole's path. It's a brutal irony. An object known for devouring light is inadvertently creating it, like a thief accidentally planting flowers in their own footprints. But the real mystery is where it's headed. Without a galaxy to anchor it, this black hole will drift indefinitely, a nomad in the cosmic dark. Could it eventually collide with another galaxy, triggering another round of chaos? Or will it roam forever, a silent predator in the void? The answers might lie in the stars it leaves behind, clues etched in light, waiting for us to decode them. This isn't just a spectacle, it's a window into the turbulent lives of galaxies. Runaways like this prove that even the universe's most massive objects aren't immune to violence, that chaos shapes the cosmos as much as order does. And as we track this rogue's journey, we're reminded, sometimes the most revealing stories aren't found in the places things stay, but in the places they flee. Among the countless star systems dotting our galaxy, Kelt 4ab stands out as a cosmic oddity, a gas giant caught in the gravitational crossfire of not one but three suns. Imagine waking up to a sky where three separate stars blaze overhead, their light weaving an ever-changing dance of shadows and colors across your world. That's the reality for this misaligned planet, a Jupiter-like giant locked in a cosmic tug of war that defies our expectations of how planetary systems form. At the heart of this celestial drama is Kelt 4a, the primary star around which the planet orbits every 3 days, close enough that its atmosphere is likely being slowly stripped away by the star's intense heat. But here's where things get chaotic. Kelt 4a isn't alone. It's bound in a gravitational embrace with two smaller companion stars, Kelt 4b and Kelt 4c, which circle each other tightly while together orbiting their primary star from a distance of about 328 astronomical units, roughly 10 times the span between our Sun and Pluto. This three-star arrangement creates a gravitational minefield for poor Kelt 4ab, which must navigate not just the pull of its host star but the competing tugs of its stellar siblings. What's truly bizarre is the planet's wildly misaligned orbit. Instead of circling Kelt 4a in a neat, flat plane like the planets in our solar system, Kelt 4ab's path is tilted at a steep angle, as if knocked askew by some ancient cosmic collision. The most likely culprit, the gravitational bullying of the outer stars. Over millions of years, their combined influence could have yanked the planet's orbit out of alignment, warping it into its current unstable configuration. It's a stark reminder that in multi-star systems, planets don't get the luxury of peaceful, predictable orbits. They're at the mercy of celestial chaos. Then there's the atmosphere. Gas giants in quiet, single-star systems tend to have stable, layered atmospheres, but Kelt 4ab's triple-star exposure subjects it to extreme and erratic heating. One side of the planet is perpetually scorched by its primary star, while the other faces the distant but still significant glare of the binary pair. This uneven heating could create titanic storms and jet streams unlike anything seen in our solar system, with winds tearing across the planet at thousands of miles per hour. Some models even suggest that the outer star's gravitational kneading might periodically compress the planet's atmosphere, triggering bursts of volcanic activity on any moons it might host, a hellish environment where eruptions are fueled by celestial tides rather than internal heat. The existence of Kelt 4ab forces astronomers to reconsider how planets form in such turbulent neighborhoods. Conventional wisdom says gas giants should struggle to take shape in multi-star systems, where gravitational disturbances would scatter the protoplanetary disk before a planet could coalesce. Yet here's Kelt 4ab, a defiant survivor, suggesting that planets might form farther out in these systems before migrating inward, or that our models of planetary birth need a rewrite entirely. This misaligned world offers more than just scientific intrigue. It's a window into the diversity of cosmic architectures. For every orderly system like our own, there might be a dozen Kelt 4ab's planets shaped by chaos, where the rules are written in gravitational turmoil and the skies are lit by multiple suns. And as we keep searching, we're left to wonder, if a planet can thrive in such a tumultuous home, what other impossible worlds might be waiting in the dance of triple stars? In the constellation Norma, nestled between the sprawl of the Milky Way's dust lanes, lies a cosmic diptych of breathtaking contrast: the Dragon's Egg Nebula and its serene celestial neighbor, a quiet giant known as HD 148,937. On one side, tranquility, an aging star enveloped in a smooth, symmetrical shroud of gas, its winds blowing gently like a summer breeze. On the other, chaos, the Dragon's Egg, a cauldron of newborn stars tearing through their nursery with violent brilliance, their fierce winds and radiation sculpting the surrounding gas into fiery tendrils that writhe like a dragon's breath frozen in time. This cosmic juxtaposition isn't just visually stunning, it's a masterclass in how stars can shape their surroundings in wildly different ways, even when born from the same stellar neighborhood. What makes the dragon's egg so mesmerizing is the sheer force at play within it. At its heart, a cluster of massive young stars, some barely a few million years old, burn with such intensity that their ultraviolet radiation ionizes the surrounding hydrogen gas, setting it aglow in vivid reds and pinks. But it's the stellar winds, jets of charged particles screaming outward at millions of kilometers per hour, that truly carve the nebula's intricate structures. These winds collide with cooler, denser pockets of gas, creating shock waves that ripple through the cloud, twisting it into filaments and knots that resemble the flickering flames of a bonfire. Meanwhile, magnetic fields, invisible but omnipotent, weave through the chaos like cosmic puppet strings, channeling the gas into delicate loops and braids that defy the nebula's otherwise tempestuous nature. The contrast with HD 148,937 couldn't be sharper. This aging star, though far more massive than our Sun, has settled into a quieter phase of life, its winds softer and more evenly distributed. The nebula around it is a study in symmetry, a near-perfect bubble of gas expanding uniformly into space, undisturbed by the violent tantrums of youth. The difference lies in their life stages. HD 148,937 has already weathered its turbulent beginnings, while the dragon's egg stars are still roaring through their rebellious adolescence, their energy remaking the cosmos around them with every passing moment. But here's the twist: these two structures might share a deeper connection than mere proximity. Some astronomers suspect HD 148,937 was once as fiery as the dragon's egg, its current calm the result of shedding its outer layers over millennia. If true, we could be looking at a cosmic before and after snapshot, a glimpse of how the most massive stars transition from chaos to order, their fury gradually giving way to elegance. The dragon's egg offers more than just a visual spectacle. It's a laboratory for understanding how stars mold their environments. The same forces at work here, radiation, magnetic fields, and stellar winds, shape galaxies, trigger new star births, and even determine the conditions for planets. And in its fiery tendrils, we're reminded that creation in the universe is rarely gentle. Sometimes it takes a dragon's fury to sculpt the heavens. Spinning through the cosmos like a tipped-over wagon wheel, NGC 660 is no ordinary galaxy. Most galaxies settle into predictable shapes, flat spirals or fuzzy ellipses, but this cosmic rebel boasts something far stranger. A colossal ring of stars, gas, and dust spinning at right angles to its main disk, as if someone threaded a celestial hula hoop through its core. This rare polar ring configuration makes NGC 660 one of the most visually arresting structures in the universe, a galactic oddball that challenges our assumptions about how galaxies evolve. At first glance, the galaxy's central disk appears typical, a dense, star-packed region with faint spiral arms, but wrapped around it like a belt is that spectacular ring, stretching 40,000 light-years across and brimming with young blue stars and glowing pink hydrogen clouds. The sharp contrast between the ring's vibrant star-forming regions and the older, yellower stars of the main disk suggests these structures didn't form together. Instead, astronomers suspect NGC 660 is the product of a violent cosmic encounter, either a full-scale galactic collision or a slow-motion theft of intergalactic gas. The merger theory paints a dramatic picture. Billions of years ago, a smaller galaxy might have plowed through NGC 660 disk at a steep angle, its stars and gas shredded by tidal forces and scattered into a perpendicular orbit. Over time, this wreckage would have settled into the ring we see today, a celestial scar from the gravitational enigma of the Great Attractor to the haunting symmetry of the Red Rectangle Nebula. these 25 cosmic wonders have taken us on a journey through the universe's most defiant masterpieces. Each one stands as a testament to nature's refusal to conform. Whether it's the universe stretching Hercules-Corona Borealis Great Wall defying the cosmological principle, the dark matter-deficient defiance of NGC 1052DF2, or the unicorn black hole sitting smugly in a mass gap it shouldn't inhabit. These aren't just celestial oddities, they're cosmic provocations challenging the very laws we thought governed everything from gravity to galactic evolution. Think about the implications. The Boots void asks if emptiness itself can rewrite our understanding of cosmic structure, while the dark flow hints at forces, or even entire universes beyond our observable horizon. The Phoenix Cluster's insatiable black hole defies growth models, and the cold spot whispers of multiversal bruises or primordial spacetime defects. Even the smallest rebels, like the featherweight neutron star Hess J 1731-347, force us to reconsider what matter can endure under extreme conditions. Every discovery peels back another layer, revealing how much we still don't know. And that's the beauty of it. The universe isn't just a static museum of predictable phenomena. It's a dynamic, evolving puzzle where every answer births new questions. The giant ark's improbable curvature, the Orc's ghostly radio rings, the runaway black hole painting star trails in its wake, they all remind us that curiosity is our greatest tool. For every mystery solved, a dozen more emerge, waiting in the depths of data or the next generation of telescopes. So keep looking up. Whether you're an armchair stargazer or a seasoned researcher, remember, the cosmos specializes in the extraordinary. Its greatest marvels often lurk just beyond the edge of our understanding, daring us to dig deeper, think weirder, and stay hungry for the next revelation. Because if there's one thing these 25 wonders prove, it's that the universe has a flair for the unexpected, and the next enigma is always just one observation away.